So at this point, you know a little bit about energy and you know a little bit about work. You know that work is this physics concept that has a very specific definition in physics that's a little bit different from the way we might use the word work in everyday life. And you know a bit about energy. You know that there are sort of two categories of energy, potential energy and kinetic energy. You know that potential energy comes from an object's location and kinetic energy comes from an object's motion. And you know that this idea of work and energy are they're closely related to each other. We said in the last lesson that work is energy being transferred either from one type to another type or from one object to another object. So with that recap in mind, what we're going to do in today's lesson is talk about one specific type of energy. This is a type of potential energy as opposed to kinetic energy. And the type is gravitational potential energy. So being a type of potential energy, we know that gravitational potential energy is going to come from an object's location. Specifically, it's going to come from an object's height. So any object that has height has gravitational potential energy, and objects with more height will have more gravitational potential energy. Now, we're going to calculate this using a formula. But first of all, before I give you the formula, let's just think intuitively about this idea of energy and height. Imagine you look beside you and you see a rock sitting on the ground. You would look at that rock and you'd be pretty surprised if that rock suddenly started to move. That rock doesn't have a lot of potential for motion. It doesn't have a lot of potential energy. And indeed, we'd probably say that rock has zero gravitational potential energy. However, if you take that rock, pick it up with your hand, and you lift it up to above your head, and it's just kind of teetering on the edge of your fingertips. You might say now that, yeah, that rock does have the potential for motion. All it has to do is slip out of my hand or have me release it, and it's going to start to fall. It's going to start to move. So by giving that rock some height, you give it the potential for motion. Once it has that height, it can quite easily start to move if we just let go of it or if it just slips. Okay, so let's dive into this formula. The formula for gravitational potential energy is PE, which just stands for potential energy, equals mgh. There are actually a whole bunch of formulas for many different types of PE. Remember, there's gravitational potential energy, there's magnetic potential energy, there's electric potential energy, there's spring potential energy or elastic potential energy. We often just use PE in all of those formulas. And the way you know, looking at this formula, that it's specifically for gravitational potential energy is because it's got this little g over here, which you'll recognize from our unit on gravity. So this clearly has something to do with gravity because it's got this little g. That's how we know this is gravitational potential energy. Okay, so the other parts of this equation are as follows. PE is the gravitational potential energy. M, as we're used to, is the mass. G, as I mentioned, is the gravitational field strength. This is that number. Remember, this is 9.8 on the surface of the Earth. And H is a symbol we haven't used yet, but H stands for height, which is pretty intuitive. There's one important thing to know about height in this equation. In that rock example, you probably, if I asked you about the height of that rock, you probably would have measured how high that rock is above the ground. And that would be a pretty logical way to do it in that scenario. But if we were to suddenly dig a hole beside the rock, now we could say, well, the rock actually could be even further down than the ground. And maybe we would measure its height from the bottom of the hole. Or if we took the rock to the ocean and we wanted to know its height, now the rock has the potential to fall all the way to the bottom of the ocean. So maybe it makes more sense to measure that rock's height from the bottom of the ocean. So it's not always obvious where we're measuring height from. Are we measuring it from the ground? Are we measuring it from the bottom of the ocean? Are we measuring it from the floor? Maybe we're on the 3rd floor of a building. One thing to keep in mind with height is this can be measured relative to wherever you want. You can measure it from the floor, you can measure it from the bottom of the ocean, you can measure it from the ground. Just be consistent for the whole problem. So for example, that rock, it wouldn't make a lot of sense if right now I measured that rock. I measured its height from the ground and said it has a height of 0. And then a minute from now, I decided I was going to measure that rock's height from the bottom of the ocean. And suddenly I think, oh my goodness, its height is so much bigger now than it used to be. That rock just gained all this height. How did that happen? Well, it didn't really gain a lot of height. I just measured it from a different place, and that would be kind of a silly thing to do. So avoid that when you're solving problems. At the beginning of the problem, pick a place, say, here's where I'm measuring heights from, and always measure from that place. Now let's look at the units of this equation. So as we're used to, mass is in kilograms. The gravitational field strength, little g, is in newtons per kilogram. And height is going to be in meters. Makes sense. Now, so the units of gravitational potential energy I can get if I multiply all of these together. So it's going to be kilograms times newtons per kilogram times meters. And I won't sort of lay this out and walk you through it step by step, but hopefully you can follow along and realize that when I've got all three of these being multiplied together, I've got a kilograms on the top, and I've got a kilograms here on the bottom of a fraction. Those are going to cancel out, and I'm just left with newtons and meters. So the units of gravitational potential energy are going to be Newton meters, which is the same as the units we discovered in our previous lesson for work. So energy and work are both measured in the same units, which are Newton meters, or you'll hopefully recall, the more common way we say that is we just say joule. A joule is the same as a Newton meter. So energy and work is measured in joules. Let's try and tackle a problem now. So a 15 kilogram textbook is sitting on a 1.2 meter tall table. The book is lifted 0.8 meters above the table. How much potential energy does it have with respect to the table? So a quick sketch here. Here's a diagram of what we're looking at. Table, 1.2 meters tall. Book, 0.8 meters above it. Now, we said you can measure height relative to wherever you want, but here in this question, it's actually saying measure that with respect to the table. So it's telling us we're going to measure our heights from the table. That's what this phrase means. This is telling me where to measure the height from. In future problems, you'll get to pick wherever you want. For starters, it's telling you to do it from the table. So let's try and tackle this. How much potential energy does this book have? Well, potential energy is m times g times h. The mass of the book is 15. Little g is going to be 9.8. And the height, well, if we're measuring it again with respect to the table, how high is this book measured from the table? That's the 0.8. So that's what I put for height. Multiply those together, I get 117.6 joules. That's how much potential energy this book has relative to the table. Sometimes I tell students that energy is tells you sort of how scared you should be of something. So imagine you're lying on the table here, and this book is kind of held just above your face. This is sort of how much damage that book might do to you. We often do measure amounts of damage. If we're looking in materials engineering, we measure damage in joules. This is kind of how much damage that book could do to you if it fell onto your face. And as you can imagine, if we raise this book higher and higher, here you are lying on the table, it could do more damage. It would have more potential energy because our H would be higher, bigger number. OK. Next question. How much potential energy does the book have with respect to the ground? So you can imagine now it's kind of like I'm asking how much damage is this book going to do? Not if it falls to the table, but if it falls to the ground. So now you're lying here on the ground. Suddenly this book looks a little bit higher, and you're a little more worried about the damage it might do if it falls down and hits you. So same idea. The book has the same mass. Little g is still the same. We're still on the surface of Earth. But now the height is measured with respect to the ground. So it's this total height from the book to the ground, this 0.8 plus this 1.2. that we're interested in. So there's my 15 as before, there's my 9.8 as before, but now the height I'm measuring from the ground, so it's the 0.8 plus the 1.2. And that gives me 294 joules. So there's the potential for this book to do a lot more damage in this situation when it falls all the way to the ground compared to the damage it could do in this situation when it just falls to the table. Okay, part C. How much work would gravity do on the book if it fell to the ground? You'll notice here we're being asked about work. Not asked for the potential energy. How much work would gravity do? So you got to remind yourself a little bit of what work is. We'll copy down our diagram again here. And you'll remember that work from our previous lesson is force times distance. So to talk about work, I need some info on forces. So let's look at the forces acting on that book as it falls to the ground. So I'm just going to do a little cheater free body diagram here. Just draw it on top of my existing diagram. As this book falls to the ground, its free body diagram is just going to look like this. There's going to be one force acting on it, Fg. And you guys know that Fg is equal to m times little g. So there's my free body diagram for this book as it falls to the ground. And I want to know how much work is this gravity force doing on the book. So you'll recall that work is force times distance, but they have to be parallel. So then I say, okay, well, which force am I talking about here? Well, I want to know the work done by gravity. So this will be the force of gravity. This is the distance that the object, in this case the book, travels. So that's going to be my 1.2 plus my 0.8, so 2 meters. And they have to be parallel. Is my gravity force parallel to the distance that the book moves? Yeah, gravity's down. The distance the book moves is down. So those two are perfectly parallel, which means this is good and I can use this equation. Now, for the force of gravity, what I've done rather than actually going and calculating the number, I've just written this equation for it in here. Force of gravity is m times g. There. And the distance is just my h from before, the height. And so this makes you realize, wait a minute, the work done by gravity is m times g times h. That's what we said the potential energy was up here, m times g times h. And so this illuminates something about potential energy. Potential energy is the amount of work that gravity has the potential to do. So this link between work and energy is becoming a bit stronger as we learn more about how these two are calculated. So now realizing I'm just doing m times g times h, the same thing I was here, I can plug through that and I'll get the 294 joules again. So 294 joules is how much energy this book has before it's dropped. And 294 joules is how much work gravity does on the book after it's dropped, while it falls. So again, the take-home point there is gravitational potential energy is the amount of work that gravity has the potential to do.